We're going to take a look at continuity of functions. We recognize that the limit is used when a function might be discontinuous to determine what's happening on the function very near an input value that will lead to an undefined output. For instance, this function that's in front of us is defined everywhere except at x equal 2. I don't know if you can see or not. This function is discontinuous at x equal 2. There is a hole in that graph. When we discuss the output of the function at x equal 2, we're going to have a problem. That is going to be undefined. There is no well-defined output. So we say this function is discontinuous at x equal 2. We know that the limit exists here because as we approach an input value of 2 from the left, the outputs are approaching 3 from below. As we approach an input value of 2 from the right, the outputs are approaching 3 from above. So we know that the limit as x approaches 2 exists, and we know it equals 3. If the function was defined at x equal 2, would it then be continuous? Let's darken in that hole. Now we have an output value at x equal 2. When I put 2 into this function machine, it yields an output value of 3. So yes, the function exists, the output does, f of 2 exists, and equals 3. So the question is now, is the function continuous? Well, this function is. A continuous function is evidenced by putting your pen on paper and drawing the entire function beginning to end without ever lifting your pencil up. So yes, this particular function, now that we have a well-defined output at x equal 2 and that output is 3, that function is continuous. Let's look at the same sort of scenario here where f of 2 is defined. We have an output at x equal 2, but it's not necessarily equal to the output that we found on our limit. Here, f of 2 exists and it equals 1. So the question now is, again, is this function continuous? Can I put my pencil on the paper and not lift it off of the paper and draw every single plot on this graph? And the answer is no, I can't. I would still have to lift up my pencil here and drop down to an output of y equals 1 in order to plot that point on this graph. So just because a function has an output and just because the limit exists does not mean the function is continuous. There are some conditions that need to be met in order to say that this function is continuous at x equal 2. So what conditions must be met for the function to be continuous, and specifically continuous at an input value of x equal 2? Continuity at a single point in the plane. Well, we said we were continuous when the limit was 3 and the output of the function was 3. So there are conditions that need to be met in order for a function to be continuous at a point. And here are the 3 conditions. When we talk about is this function continuous at a certain value of x, here we're talking about where x equals c. Let f be defined on an open interval containing c. We say f is continuous at c if these 3 conditions are met. First of all, the output exists. F of c must have a corresponding output of some real number. It cannot be undefined. The overall limit, this is not a one-sided limit, this is the overall limit at c for that function must exist as well. We'll call that t. These two things, number 1 and number 2, must be equal in order for the function to be continuous. In other words, if this was the case, if f of c was k, and the limit as x approaches c of f of x was t, we would not be continuous. The only condition under which this function is going to be continuous is for those two things to equal the same value. If even one of these above conditions fails, even one, if 2 holds and 1 fails, if 1 holds and 2 fails, if the function output exists and the limit exists but they are not equal to each other, this function is discontinuous at that value of c. Verbally, we would say f is a defined function over any open interval that contains c. F is continuous if f has an output at c, the limit exists at c, and the limit at c is the same as the output at c. If the 3 conditions are met, f is continuous. If not, this function is discontinuous. Now, continuity at a point is different than continuity over an interval. This is exploring what's happening at one single point in the plane. Continuity over an interval of input values is different, and we explore that differently. So most familiar functions used in the text are continuous. At least they are continuous on some subset of the real number set. It is necessary to use the behavior that you know from your previous math work, and our parent functions are going to be a big part of that when a familiar function is not continuous. For this function, f of x equals the square root of x, this function is continuous over the interval of all positive input values and 0, when x is greater than 0 and equal to 0. If I were to ask you to show that this function is continuous at x equal -1, you're going to have an issue. This function is not continuous on a set of numbers on an interval that includes -1. However, if I ask you to show that this function is continuous at x equal 1, you could clearly do that. You could run through 1, 2, and 3, that 3-step process for continuity at a point, and this function would pass that test. For this reciprocal parent function, we're going to have issues about being continuous on an interval if that interval contains the input value of 0. This function is not continuous when x equals 0, but it is continuous over any interval that does not contain x equals 0. This function is not continuous over this interval, but it is continuous over that interval. So it becomes very important that we understand continuity at a point, that 3-step process that we just looked at, and continuity over an interval of x values. Here are the graphs. Of course, the square root function is a smooth continuous function over its domain. So if we are looking for any particular x values inside the domain, this function is definitely continuous. But if we are outside the domain of this function, it's going to fail continuity at any of those given points. For this function, we are continuous everywhere except x equals 0. So continuity of function operations. If I have two functions f and g, and I can determine that they are continuous at the input value x equals c, then all mathematical operations that we talked about in the main limit theorem, addition, subtraction, multiplication, division, raising things to a power, even a fractional power, all of those mathematical operations listed in the main limit theorem mean that the result of the operation, the mathematical operation done on those two functions, the continuity will remain. If f and g are continuous at x equals c, f plus g must also be continuous at x equals c. F divided by g must also be continuous at x equals c. Continuity of function composition. If f and g are each continuous at c, then so is the composition in either direction. If f and g are both continuous functions at x equals c, then these resulting compositions are also continuous at that same input value of x equals c. When we talk about continuity over an interval, the idea of a function being continuous at a point, fairly straightforward. So let's talk a little bit more about continuity over an interval. This function is continuous over 3 separate open intervals. The only values in the real number line where this function is not continuous are x equal -1 and x equal 1. We have a hole in the graph. The output of the function does not exist there. That's one of the 3-step process where continuity fails. The output of the function must exist, and this does not exist, and the same is true for f of 1. So it fails that step in the continuity at a point process. It will fail it for x equal 1 as well. But any other x value that I want to look at, any other real number value, it doesn't matter. If I run through that 3-step process on any other x input value besides -1 and +1, this function will pass the continuity test at all of those points. So this function is continuous over these intervals, and these are open intervals. Remember, our graphs, even though it doesn't show it, do continue on there. Here is continuity over a closed interval. Remember, there is a 3-step process. The output of the function must exist. The limit, as x approaches that input value for the function, must exist. That has to exist. This has to exist. And what's listed under 1 must equal what's listed under 2. That means we're continuous there. We can clearly see we're continuous at all points in the open interval. We will pass all 3 of these steps for any point in this interval. So the question is, why include the endpoints? Will the endpoints, will x equal -1 and x equal 1 pass this test? And we're going to pass this test because, yes, number 1 is true on both of them. F of -1 exists, and it's +1. F of +1 exists, and it's also +1. When we talk about the overall limit as x approaches -1 for this function, we do have an issue. We do have a correction that we're going to have to make. This function is right continuous. The right-handed limit exists, and it is 1. As we approach -1 from the right, the outputs approach +1. So we call this right continuous. And just in the same vein, at x equal 1, the left-handed limit, the left-sided limit for that function exists. So I can talk about what's happening approaching 1 from the left. As I approach 1 from the left, the outputs approach 1 from below. Those two things are equal. That is right continuous. This is left continuous. So we may have to qualify what kind of continuity at a given point, but most of the time we don't. Most of the time we're exploring what's happening to the overall limit.